Welcome to Secure Software Development. We begin, as we always do, in the year 2012, or 23TS. A number of things happened that year. Voyager 1 became our first interstellar probe when it left the solar system. The end of the Mesoamerican long count calendar occurred, and thus, obviously, the end of the world. Windows 8 was released. It forever transformed the way we look at operating systems. No more start menu at the bottom and icons on the screen. Now it's all tiles that you interact with. Curiosity landed on Mars. Taylor Swift released Red. And the end of the Time Wave 0 countdown happened, and thus the end of history. Lots of things happened. In addition, Apple released iOS 6, the operating system for the tablet and the phone. And this release was much heralded. We can't wait for hundreds of millions of iOS users to experience the incredible new features, including the new Maps app. So said Scott Forstall, Apple's Senior Vice President for iOS software. Great. It was a major revision to iOS, and it had some bumps. For example, Apple Maps left people stranded in the desert in Australia. It couldn't find emergency rooms for people, and it sent lots of folks in the wrong direction. It was an immature product. It was released too early. And, Apple, fortunately, learned a lot from this terrible disaster and fixed a lot of stuff. So, there you go. iOS 6 happens. There's a little glitch, but Apple learns a lot from it and grows as a company. A couple years later, Apple releases iOS 7, and then in 2014, or what would that be, 25TS, Apple releases iOS 7.06, and it also releases iOS 6.16. And these are of note to us because they're released to address a specific CVE, namely the one shown there, CVE 2014-1266. This was an issue introduced in iOS 6, and it persisted, as you can tell, for a number of years into iOS 7. It was a vulnerability that allowed a man-in-the-middle attack against Transport Layer Security, or TLS, not TLC. TLC is a musical group that was popular around this time, maybe waning popularity in 2014, but not Transport Layer Security, which was actually TLS. TLS is the backbone for implementing the secure version of the Hypertext Transport Protocol, which is what underpins the entire web. So, what was this vulnerability? Well, if you go look at the National Vulnerability Database, it will say the such and such key exchange function in this feature, etc., allows man-in-the-middle attackers to spoof SSL, Secure Certificate Layer, servers by using an arbitrary private key for a signing step or omitting the signing step. That's not super helpful. We can take a look at the metrics, so we can see that this had a base score of 7.4. That's pretty high. It rates the color red on the National Vulnerability Database. We just don't throw the color red around willy-nilly. Right, that's reserved for things that are special. So what was it? So let's see. Look at the code on the right and see if you can spot the weakness. So you should pause the slides here, or pause the video here, and take a look and see if you can spot the weakness in the code. I think you'll be able to, even if you're not sure what's going on. I think you'll catch this one. So go ahead and pause and look for it. Did you spot it? You probably did. It's right there. It's that weird second Goto fail. And, despite the indentation, it's not part of that if, right? You know how C works. I have an if statement. I have a predicate in parentheses followed by the body. Typically, I would put something inside curly braces, but I don't have to. I can put a single statement on that line, terminating it with a semicolon, which terminates the entire if. So the if ends after that first Goto fail. The second Goto fail is outside the if, so it's unconditional. So what that means is, we come along, we evaluate these. These are all about updating a hash by adding some information to the hash. If something goes wrong, we go to fail, and we set the error code gets set. Here we just go to fail. So we skip over finalizing the hash, doing the SSL verification, and checking it and reporting an error, and we come all the way down here. Well, going to fail must mean we fail, right? It must mean we've failed. Well, let's assume that this hash stuff is all working just fine. So we update a hash, update a hash, update a hash. How would it fail? I guess it would fail if it couldn't get memory, I guess. So assume these don't fail. Error is set to 0. We then unconditionally go to fail. What does fail do? It frees the buffer and it returns error, which is 0. Okay. And this is part of the code that verifies the SSL signature. Right? If something had gone wrong, we would have detected that because error was non-zero. If we didn't have this Goto fail here, we would have finalized the hash, and then we would have done the verification, and the error code would have been written to error. And if it failed verification, we'd write a message and then go to fail and return the error code. And if it succeeded in verification, we'd get back error equals 0, which we'd return indicating that it succeeded. So what happens is we come in here and we always go to fail, which means we always succeed. Verification of the certificate always succeeds. In fact, verification never happens. This code just always reports that verification has succeeded. Well, surely that's bad. It turns out that it's pretty bad. It's a case of unreachable code, right? All the code that does the actual work is unreachable code. And it turns out that compilers have options sometimes to catch things like unreachable code. So the GCC compiler has the option -w unreachable code, and that will report any instance of unreachable code if it were implemented. But it's not. It was removed in 2011, and there's a link to the message where they report it being removed in 2011, right? Over a decade ago, it was removed. It still accepts the option and quietly doesn't check anything. So the code above that, over on the right-hand side, is very simple code with an obviously unreachable print statement and return, right? Go to end is going to skip over those and return 6. If I compile that with GCC with the unreachable code flag, it will compile it just fine and give me no warnings, and it will run, and I'll still have unreachable code. That's not great. They could fix that. It's been over a decade. What about Clang and LLVM? It also has that option, but it seems to work. So look over on the right, you'll see we try compiling the same code, and it says, hey, this code will never be executed. And it gives us the print statement as an example of code that will never be executed. Okay. Oh, let me go back one. So, as a fun exercise for you, people who are fortunate enough to be listening to this little recording here, try the code and try Clang over there on the right and comment out that print statement. The return 5 statement is still unreachable code, right? See if Clang reports that it's unreachable. Just a little test for you to perform. All right. Coding standards might save us. And in fact, in this case, coding standards would probably have saved us. Most coding standards require that you put the curly braces around the body of an if statement and while loop and so on. You don't just have the naked thing out by itself. It's very, very common. In fact, some editors will insert that for you, assuming you always want it. Okay, a coding standard like that would have actually fixed this issue, because the two Goto fails would have been inside the curly braces, and the second Goto fail would have been unreachable code, and it would have been just fine. We would still have had that weird Goto fail in there, but it would have been okay. Not every coding standard has this. In particular, the Linux coding standard says not to do this. But in this case, I think they're wrong, because this is clearly something that would help you catch these kinds of errors. This became known as the Goto Fail Bug for obvious reasons. There's even a song for it. This is not a video with the song. Go look the song up on your own. This is a video that explains the Goto Fail Bug, and it's a pretty good video explaining it. What does this mean for software development? Well, test, and test for failure. If you write code to validate a certificate, you should test that code with a valid certificate and with an invalid certificate. A simple test to see, what does this do when does it fail when it should fail? That would have caught this. Testing would have caught this. Test for failure, right? If you're building a mechanism in there to, especially something to test a security property, test for that property failing, okay? And then the other general stuff, right? Adopt coding standards that can reduce your risk. Default to failure. This is an important one. This also would have saved the day. Error throughout there was repeatedly reused, and it was always going to be set to pass. And we saw this with the little example of the password, the buffer overflow. It's a password. Because we assumed everything was fine unless we set something to bad, I think that was the case, there was a problem. So assume failure. Default everything to failure, and only, if and only, all the tests pass, then set your flag to success. If we'd done that in this code, it would have, we would have skipped over the part where the flag was set to success, and we would have returned an error, and every certificate would have failed, including valid ones, because we were skipping over the validation step. Default to failure. This is sort of the equivalent of deny all when you're setting up a firewall. Review your code. Suppose a human being with eyes in their head had looked at that code. They would have seen what you saw, which was a weird-looking thing of two Goto fails, and they would have caught it. Almost certainly. Right? Testing would have caught this. A coding standard would have caught this. Defaulting to failure would have caught this. Reviewing your code would have caught this. This error should never have happened. Construct tests for failing conditions, not just success. Coding standards, use them. I give you some links to them right here. The Mozilla Style Guide, the Recommended C Style Guide, and Coding Standards. Those explicitly say, hey, go and use this. And there's good reason to do this. If you're working together on a project with other people, code merges can actually introduce this problem, right? Because it interleaves lines from different authors, and it can prevent problems like this from happening because it creates that guarded context, that code block. Okay. Make the default error code an error. Do not set error to 0 until and unless the final check succeeds. Fail fast. And review code. There's lots of reasons to review code, not just catching errors, but also people learn from one another. Let's look at each other's code. That gives you an opportunity to make recommendations to the author. That's good. To learn from the author. That's good. Right? Everyone gets better. Everything benefits from it. And I've done tons of code reviews in my time, and they can be boring, they can be interesting, they can be fun. You have to get into a mode where you do this, and not have it just be a death march, but talk through the process of building the code, and talk through it with some other people in the room. You don't have to go through every single little symbol. People are going to look at it, they understand the code, and they're going to catch this kind of thing. All right, so let's talk about some information security properties. Now, you've all seen this, right? You've seen the CIA triad: confidentiality, integrity, and availability. Critical information security abilities or properties that we want systems to have. We want confidentiality. We want information controlled so that it's not shared with someone who shouldn't have it. We don't just send your private information out into the world. We have some degree of confidentiality so that the information is controlled. Integrity: the data that's being used should be authentic, accurate, and reliable. And it may seem like those are all saying the same thing, but they're all subtly different from each other, right? Authentic information is the real stuff. Accurate information is the correct stuff. And reliable information is the trustworthy stuff, okay? And all together, those tell us that we have data integrity. Availability: systems should be functioning, and it needs to be working, and it needs to be useful. We need to get work done, right? Availability used to be the overriding concern, probably still is, for telephone switches. You want absolute availability. You want 5 nines, 6 nines, 9 nines, as we would say, of availability. So when someone picks up the phone, they get dial tone. When they dial a number, they get a connection. When they dial their cell phone, they get through. You want full availability. These are the kinds of properties we want an information processing system to have. It's good with the information has integrity, and the whole system is available to do the work. But bear with me. I mean, maybe we should say something about utility. We didn't really talk about whether the whole thing is useful. We said it's available, data's good, we're preserving confidentiality, but I mean, hopefully it's fit for a purpose. I mean, you can imagine 2 different systems, one of which is really, really hard to use, maybe even borderline impossible to use, and it's so problematic to use that it can encourage bad behavior, which can undermine security. Well, that's bad. It's better if we have utility so the system is much easier to use, right? Data must be useful to the purpose at hand, right? The data that's in the system is the data we need. It's not some other data. And the system itself is useful to solve our problem. Okay, fine. Now we have 4 things. The CIAU, I don't know, we want to call this quadrilateral? Sure. Oh. What if, hang with me, what if we pulled authenticity out and said, hey, let's promote that up to a higher level. So now it's confidentiality, integrity, availability, utility, and authenticity, right? The data has to be from the correct source. We pulled it out of integrity and promoted it up. All right, that's great. Now notice I've labeled 2 of the vertices, but if I could find some way to label that 3rd vertex, that would be cool. So, possession. Authorities must maintain positive control over the assets. That's different from confidentiality. Okay? That's different from confidentiality. Slightly different concept here. And that gives us 6 things. And that's not a triangle anymore. That's a hexagon. Well, it's actually called the Parkerian hexad. And it was proposed by Don Parker. He passed away in 2021. And it was proposed by him in 1998. And you can see over there, utility, confidentiality, possession, integrity, authenticity, and availability. This is a different way to look at the properties of a secure information processing system. All right, great. So now we have those. What else? There's something called the 4-step security model. Not that widely used, but it's interesting. It's 4 A's, 3 AUs. It's questions that you should ask, that you should evaluate before you perform some action or you grant access. So the system should verify, who are you, right? Who are you? Know your user. Who are you? Are you allowed to do the thing you want to do? Are you authorized? Okay. Is the data that is needed to perform the action that you are theoretically authorized to perform, is that data accessible? And is the data intact? We ask those questions, and yes, we know who you are. You are, in fact, authorized. Data is available, and it's intact. We are then able to correctly perform the action and give you back a result. This has been heavily critiqued. I've got a link to a critique of it on Bruce Schneider's blog. You don't see this much anymore. It's of more historical interest than anything else. But again, you see these properties, and you'll see them up again. You'll see authentication, availability, authorization, authenticity come up in different contexts. The most commonly used now model is really this one, I think. It's the AAA model. So we still have the usual ones: confidentiality, integrity, availability around the outside. But you'll notice we have 2 more on the inside. We have authentication and non-repudiation. Authentication says, I have taken steps to verify that you are who you say you are, right? Know your user. You've been positively identified by the system. Non-repudiation says, you can't do something and then say you didn't do it. Okay? You can't say that action wasn't taken by me. I didn't delete this or add this record, right? That wasn't me. So non-repudiation says that a sender, someone who's doing some action in the system, must not be able to deny sending a message that they sent. Non-repudiation will show up quite a bit when we talk about information security models. All right, there you go. Now you're all caught up. You have in your mind this set of ilities. There's a lot of them. Maybe there's 3, maybe there's 6, maybe there's 4, maybe there's 5. There's some number. And with all that in our head, let's begin to think about how we would model security. We haven't talked about what security explicitly is. Hopefully by now you have a good sense of when you're seeing security and when you're seeing something that's not security. You have some notions about how security behaves out in the world. But let's talk about models. People have tried to build models to be able to analyze systems and analyze the security of systems. When you're engineering something, one of the first things that you'll often do is you'll figure out, okay, this is my system that I'm going to design. This is my system boundary. These are the external forces acting on it. These are the forces in opposition, etc. You begin to draw where the moments are and put everything you know into a picture. Then you can analyze that to figure out what happens with the system. But basic freshman statics and dynamics in engineering. In this case, we want to do the same thing, but we want to try to find a way to do that for security. So it helps now to ask, what is security, right? I mean, we're pretty deep in the class. In a class with security in the title, or at least secure in the title, we probably should think about what security is. So one way to think of security, not the only way and not the perfect solution, is we could say something like, security is the ability to control who has access to a thing. And that thing could be a location, could be like you build a fence around your yard to keep the neighbor's dogs out. Okay, that's a kind of security. It could be an object, right? We're trying to keep the crown jewels protected from theft. You can go to London and go see the crown jewels, but hopefully you can't get to them and take them and walk out with them. It could be a person, right? We have security around Taylor Swift when she comes and goes from her concerts because she's a national treasure. Similar here in America to the crown jewels in England. It could be some data that we want to protect, or any of those things. Something that we want to control access to. Now, the definition up there depends on access. What does that mean? What does it mean to access a thing? And control. What does it mean to control a thing? And a lot of the models we're going to look at will give you answers to what constitutes access and what constitutes control and how they interplay with one another. If you wanted the thing over on the right that's one of those HID scanners you see that you tap your card and open a door. This one had the screw brake on the bottom, so the whole panel could be removed. It was kind of fun. Now that we have a sense of what security is, we can ask an, I think, interesting question, which is, what is destruction the same thing as security? And we'll see an example of this much later in the class when we go through the case study. So, if something is destroyed, can we claim that it's secure? And it's kind of a philosophical argument, but my point of view would be, if a thing doesn't exist, we can't really talk about its security anymore, right? For security, we assume someone has authority to decide who has access, right? Control and access. And the set of people who have that authority and the set of people who therefore will have access is non-empty. If we destroy it, those sets are empty, right? The reason we shred papers and erase hard drives and do all the other things we do isn't to secure those things. It's to secure the data that is on them. And presumably there's either other copies of that data, or we want to forget that data and make sure that no one gets a copy of it. Presumably it's in someone's head somewhere. Let me go back a slide. Over on the right-hand side is a bin. This bin has a padlock there, and I expect you could pick that padlock. But it's got a slot up at the top, and that slot is where you drop papers. And the papers go in there, and eventually the whole bin is wheeled out and shredded. It's a shred bin. There are burn bags. There's a whole bunch of other things that are security controls to protect information security, and they depend upon destruction to accomplish their security mission. So once you drop some paper in that slot, you're never getting it back out. It's in there until it's destroyed, and there's nothing you can do about it unless you buy one of those flexible grabbers you see over on the right-hand side there, but they're prohibitively expensive, right? You want to buy, and I don't understand their pricing. So let's take a minute to think about the economics of this. So I buy the 35-inch one, and it's $11, or I can buy the much longer 79-inch one, and it's only like $8. What's that about? How does that work? Anyway, neither here nor there. The flexible grabber is great because now you slide that little grabber down through that slot, you grab onto some stuff, and you pull out some papers. Voila, secret's achieved. So information security, our definition of information security, really doesn't say anything about whether a particular thing actually is secure. And that's because security is in flux. It doesn't give me a way to say this is secure. It doesn't say, oh, this laptop is secure because this definition applies. Because it's hard to know that sort of thing. And also, you have to realize there's incentive. If stuff has value, then there's incentive to find ways to violate security and to achieve whatever access you need to get paid or get secrets or do whatever it is you want to do. And so the notion of security is always evolving as information about security and how to defeat it gets out into the world. There are many different contexts for security. And there are many different kinds of things to secure. There's many different reasons to secure things. And there's lots of different outcomes when security is violated. Security could be violated for an information processing system, which could lead to someone's identity being stolen. Security could be violated for a government data processing system, which could reveal the names of covert agents and get them killed. Security could be broken for a mechanical system or a manufacturing system that could damage stuff that's being built, possibly even kill someone. So there's many different types of consequences, and it's instructive to look at one set of these. And so over on the right-hand side, you see some stuff about national security information. This is NSI. We call it NSI here in the United States. And we have basically three different layers of classification. Top secret information resulting in exceptionally grave damage to national security if revealed. Secret, serious damage, and confidential, just causing damage. And you may wonder what constitutes exceptionally grave versus serious versus just damaging. And there are guidelines for all of that as well. Don't want to get into that. None of us want to become a original classifier or a derivative classifier, I don't think. So, there you go. Well, that's where we'll stop this analysis. But there are these different security contexts, and over here you can see top secret is the highest level. Below that is secret, and below that is confidential. We'll come back to that, and we'll use that ranking a little bit later on. So a security model is there to add some rigor. It's there to let us nail down a lot of these vague things we've been talking about, like control and access, and begin to describe a system and its security policies more precisely, and to maybe even analyze them and demonstrate or show maybe even mathematically through proofs that we achieve some layer of security if our assumptions are true. Important point. There's always a set of assumptions around whatever you're doing. If those assumptions are violated, maybe you can violate security even though everything else holds true. Right? The math may all still work, but before you get to the math, you have to make a series of assumptions about the system. All right. Let's talk about some of these models. Now, if any of you have done the CISSP, or you're thinking about doing the CISSP, or you're studying for the CISSP, you'll have seen some of this already. So I apologize if this bores you, but I think it's instructive and interesting. The Bell-LaPadula model, and it is LaPadula. The Bell-LaPadula model is a model that really focuses on confidentiality. It was created by David Bell and Lynn LaPadula for MITRE, and they created it under contract for the Department of Defense. And so you can guess the kinds of access classes the U.S. Department of Defense cares about, right? Top secret, secret, confidential, what am I trying to say here? Unclassified. There we go. That's what I want. Unclassified, etc. So the Bell-LaPadula model is a multi-level model of security that structures information into access classes. Okay? And these can be in a total order. For example, top secret, secret, and confidential are a total order. Right? Top secret at the top, secret is in the middle, confidential's at the bottom. An object has an access class, and it contains some information. So, for example, an object is a file. A subject has an access class and can read, write, or both read and write. So a subject is a user, or it could be another information processing system. But for simplicity, just assume subjects are users, objects are the files that contain the data. The Bell-LaPadula model focuses on the container of the information and not the information itself. That's an important distinction. It doesn't try to reason about the information. That's hard, right? It's hard even for people whose job it is to do that. It's hard for derivative classifiers, original classifiers. These people make classification decisions. You may wonder, how does something get classified top secret? Someone creates a classification guide. Those guidelines are then applied to determine what the appropriate level of classification for a piece of information should be and for how long it should be classified. And typically that would be a derivative classifier or an original classifier who would make those decisions. Which one it is depends upon where the information comes from. I don't want to get into all that. So focusing on the container, focusing on the access class for an object and the access classes available to a subject. In fact, the Bell-LaPadula model tries to formalize all of this. And really quickly, because we'll use some of this language a little bit later on, we let L denote the set of all security values that can be assigned to sensitive information. What's L? We'll define L here. Bell and LaPadula define L to be C cross the power set of K. Okay, so what is C? C is a finite, totally ordered set. And in fact, for most purposes, C is the set you see over on the right. Top secret, secret, classified, and unclassified. Right? That's a totally ordered set. Top secret is the most restricted, then secret, then classified, and then unclassified is the least restricted. Totally ordered set. And P of K is the power set of another finite set, K. What is K? K is all of the additional code words and compartments and so forth that apply to information. They're additional constraints. And here in the U.S., with our system, we might have no foreign, meaning I can't release this to a foreign agent. Rel to UK, meaning I can release this to the United Kingdom. SIG, which tells me something about maybe the source of the information. And there's a ton more. Some of the categories are actually themselves classified. Some of them have been declassified, are publicly known. Some of them are not publicly known, etc. There's a whole bunch of them. It's maybe the case that nobody knows all of them, right? DOE has its own classification system. DOD has its own classification system. There's overlap. There are, I can't think of the word here that I'm trying to think of where you pass stuff back and forth. It's not coming to me. But, for example, DOD has top secret, secret, classified, and unclassified. DOE, which manages the nuclear secrets, has Q and L for their clearances. Collateral. That's what I'm trying to think. Oh, what is collateral? There's some collateral stuff so that we can pass information back and forth. And then there's a whole raft of other stuff out there in the world. So, a security value is a cross product. It's a combination of one of those elements from C, like top secret, and 0 or more of the elements from K. So it could just be top secret, or it could be top secret, no foreign, or it could be top secret and TK. Any of those sorts of things. So, for example, you might have a classification like you see over here on the right. Top secret, SIG, no foreign. So that has the little total order element, top secret, and then some additional classifiers over here. I'm telling you all this not because I want to bore you with our classification system, because you need to know this to really understand why the Bell-LaPadula model is built the way it is. So a security value is an ordered pair, right? V, a security value, consists of one of those things from C and 0 or more of the things from K, some subset of K. Now, given that, we can say one security value, C1K1 dominates another security value, C2K2, if C1 is greater than C2. So top secret dominates secret, and secret dominates classified. But in addition, we need to say something about all the code words. And what we have to say is the code words for the one that dominates have to include all the code words for the ones that they dominate. So, for example, if it's top secret, but it's compartmented, then it can only be dominated by something that is also top secret that has the same compartments, right? So if I want to look at stuff that is top secret in compartment X, then I need to have a clearance that is top secret, but also grants me access to X. All right. To implement all this, we give every container an access control list that specifies who has what access to the file contents. Now, the model has to be simple, or we're going to rapidly get into a state where information can be leaked or access can become uncomputable. We talked about how when you increase the space in which you can configure things, eventually you become so configurable that you run up against the halting problem, and it becomes difficult to prove some property like halting or security, maybe even impossible to prove it. If we keep things simple, then we can do proofs, right? Everything is, for example, provable in the world of finite automata. But when you allow infinite state space, like a Turing machine, suddenly you have a lot of undecidability crop in. So the Bell-LaPadula model follows the DoD guidelines of strict levels to try to avoid this problem. Now, let's get into the first property. The simple security property says a subject, right, a user or another information processing system, can only read an object file containing some information if the access class of the subject dominates the access class of the object. So if I have a top secret clearance, I can read top secret documents. If I have a top secret clearance, but I don't have access to compartment X, I can't read top secret documents that are in compartment X. I have to have all those little pieces. So I'm allowed to read from anything that my class dominates, but I can't read up. I can't read to things that dominate my class. So I can read down, I can read lower level stuff, but I can go read, I'm top secret, so I can read secret and confidential, but I can't go up. I can't read something that's top secret and X, because I don't have access to that. So I can read down, but I can't read up. And that's a simple security property. But what if, so let's say I have a secret clearance. So I can read secret material. What if I could what can I write to? I can write to secret documents. Could I write to classified documents? Right, classified is lower level than secret. So suppose I read my secret documents and then I write into a classified document or even into an unclassified document, and now I've leaked some secrets out. That's bad. So let's institute an additional rule. We'll call it the star property. And we'll say, okay, you can write up, but you can't write down. So you can write into documents at your own level, obviously, and you can also write into documents at a higher level, but you can't write into documents at a lower level, because if you could leak information out. So what does this mean? This means I can read down. Let's say I have a secret clearance. I can read secret material and I can read classified material, but I can't read top secret. Fine. I can write to top secret or secret, but I can't write to classified. So over time, what this means is information drifts up. Information tends to be classified at a higher and higher level, perhaps higher than it should be. It's called overclassification, and it's a real problem. So that's bad. As information drifts up, it may go to a place where it's not necessarily useful anymore because I need people to have access to it, and I need to move it back down. So I need a privileged user in my system who can, in fact, write down, or I'll never get stuff back to a level where it becomes useful. Now there's the strong star property. Can I have both read and write access to stuff? Well, only stuff at my own level. I can't have read and write access to stuff that's above me or stuff that's below me, because reading stuff above me, that breaks the security property. I'm reading stuff I shouldn't have access to. Writing the stuff below me means that I could leak information out. So if I have both read and write access, it can only be the stuff that's at my own level. This model provides what we call mandatory access control. What does that mean? That means that there is somebody who mandates what the access control is, and it is centrally managed. So there's a central authority, and again, DoD, very much a central authority-driven organization that mandates how access control is performed and implemented. This can be distinguished from, maybe passing some of those decisions down and saying, you have the right now to make decisions about who can access your stuff. That would be something called discretionary access control, where access control is distributed down. But again, the Bell-LaPadula model is mandatory access control, very centrally managed. It's a formal model. I've already showed you a little bit of that earlier, but there are theorems proven. The model was described mathematically. There are theorems proven in the paper. It allows for some very strong statements. Now, here's a question for you. What happens if an object in the system changes its access classification? So, for example, I say, well, this was merely secret, but now I'm going to move this information to top secret. Okay. People with a secret clearance might have cached copies lying around, and now they have access to a document that's top secret, and I violated the simple security property. Okay, that's bad. It was unclear how to handle all this. And so they brought this up as a question when they were building the model. And David Bell recounts what happens. He says, we were directed to exclude dynamic changes of classification. The direction to exclude dynamic changes seemed to remove all interest in the problem. It made it a very static problem. And since that's not necessarily realistic, right? In the real world, things change and move around. It seemed to be a less interesting problem. But they gave it a try, and they tried to codify that property, this property of things not moving around. And they called it the tranquility principle. And they had two versions of it. The strong tranquility principle prohibits any change in classification levels while the system is operating. So you turn it on, people can access stuff and do stuff, nothing can move around. That's probably too strong. So they also had the weak tranquility principle. This prohibits a change in classification that would invalidate a security policy. So all the cached copies have to be erased or returned or whatever, and once no one else is accessing a document, you can then change the classification of that document. But you can't do it while someone has access to it, because that would violate a security policy. So the weak tranquility principle is a more realistic way to deal with that. Now, the original paper is of interest. It's linked in the notes at the end of these slides. It uses a lot of important security concepts, and you'll find a lot of this in the Orange Book. The Orange Book is shown over on the right. It is a really foundational book. You'll find it mentioned a lot. You'll find a lot of people who will, still to this day, who will talk about it, right? The Orange Book for a long time was the way in which we discussed evaluating and understanding how to build systems that had some security. Multics is an operating system. It persisted sort of formally until around 2000. It's still around in a variety of other forms. A lot of innovations came out of Multics, but it was based around this type of centrally managed security model. Now, here's a question. Is this model the end-all, be-all of security? Are we done? Have we solved security with this model? Well, the model focuses on confidentiality, but it doesn't address integrity. It doesn't say anything about whether the data is valid. It doesn't say whether the data is available. It doesn't say doesn't address all the other illities we saw at the top of this lecture. And it's inflexible. Remember utility from the Parkerian hexad, right? If we want to write down, I got to get a super user to do that for me. And that theoretically introduces a single point of failure. There's problems. It doesn't address data aggregation and data and metadata problems. What do I mean by this? It is the case that there is unclassified information anyone's allowed to have. And there are unclassified tools anybody can grab and use. And it's all unclassified. But if you find out that a particular agency is using a particular tool or set of tools, and they're using them with a particular set of data, that piece of information may be classified. None of the components is classified, but when you aggregate them together, you have information that we want to protect. You have classified information. And so the aggregate data can be classified at a different level than the individual components of that. The metadata problem is another problem. The data itself may have a classification level of, let's say, secret. But information about the data, namely something like how you obtained it, that may be classified at a much higher level, right? The data may be secret, or maybe even unclassified, but the information about how you obtained it can be top secret. And we found when the U.S. photographed Cuba from satellites, they found missiles. The fact that they had identified the missiles in Cuba, started the Cuban Missile Crisis, was unclassified. It was on the news. But the specific methods, the details of the spy satellites, of the cameras, of the optics, and of the methods they used to find this stuff, that was all very heavily classified. Doesn't address those issues. And of course, it's a mathematical model, and some people think math is hard. So Bell-LaPadula is probably not the end-all of security. So confidentiality focuses on keeping secrets and limiting access. Bell-LaPadula does that in spades. It focuses on confidentiality, ignores almost everything else. And this is, in fact, the right approach for some systems. You can imagine some systems, right, trying to keep your typical classified data. This is a good way to do that. This is a good way to think about it. It's a good way to reason about it, and it makes sense. So it's a right approach for some systems, but not necessarily for everything. And that brings us to the Biba model. So the Biba model is another model, came out a little later than the Bell-LaPadula model. And it's also one of these centrally managed models. But instead of focusing on confidentiality, the Biba model focuses on trust, or I should say integrity. So it focuses on the I part of the CIA triad. It focuses on integrity. So we organize trust into a hierarchy just like we did for confidentiality. Up at the top of the hierarchy, the most trusted sources. Down at the bottom of the hierarchy, the least trusted sources. So we have a rule, and the rule is an object is only as trusted as the lowest level user who has write access to it. Here, level refers to level of trust. So we've got a file. I can edit the file, and maybe you trust me. And let's say, pick a name. Jennifer can edit the file, and you don't trust Jennifer at all. In fact, you think she's trying to undermine you. As a result, the file itself is now suspect because it may have malicious changes from Jennifer. You trust me, but you can't trust Jennifer. So the file is only as trusted as the least trusted user who has the ability to write to it. Okay, keeping that in mind, we'll see how that plays out as we build out the Biba model. The first thing is the simple integrity property. A subject can only read an object if the object dominates the trust class of the subject. You can read up. I can read more trusted material, but I can't read less trusted material. I'm allowed to read, say, a report from the Associated Press, but I'm not allowed to read the Gateway Pundit, right? Associated Press is a very highly respected, occasionally wrong like everybody, but a very highly respected, very trusted source. The Gateway Pundit is an extremely untrusted source. Wikipedia has a whole set of discussions on the Gateway Pundit. Could they have stuff that's right? Sure they could, right? Could the Associated Press have stuff that's wrong? Sure. But in general, the trust class associated with the Associated Press is high. The Gateway Pundit is low. If I go read that Gateway Pundit stuff, I may have a bunch of stuff now in my head that's polluting my view of the world because I have all this stuff that's untrustworthy, but I can't help but think about it. And so I don't want that to happen. I don't want our users or other systems to process unreliable information at a higher reliability level, right? So I'm a trusted source, but if I have bad data, I will become an untrusted source myself. Make sense? So you can read up, but you can't read down. Likewise, right? I'm trusted, let's say, to a medium level, but Terry is trusted at the highest level. Can I write into Terry's documents? No, because I'm not as trustworthy as Terry is. I can write into Jennifer's documents because I'm more trustworthy than she is. So I can write down, but I can't write up. I think that makes some sense. Hopefully this is all making sense to you. And of course, the strong star property, again, I can only read and write to documents at my own level. This is another level of mandatory access control. Centrally managed, someone has decided these are the levels, these are the trust levels for each individual, etc. Mandatory access control. Is this model useful? Well, the concepts in this model show up in a variety of places. FreeBSD is one. There's a secure operating system for BAE. That's what the boat picture over on the right refers to. It's actually the one on the right is actually the Pitbull operating system. And the thing that they're trying to emphasize here is that we have strong trust relationships among components, and as a result, we can contain damage. Bad information flows into the system, but it can't flow up to these higher levels of trust because it's prevented from doing so. So damage to one part of the system, untrustworthy, bad information, can't propagate through the system. Integrity is all about assuring the information is trustworthy and accurate, and Biba focuses solely on integrity. And this is, in fact, the right approach for some systems. Right? For some systems, this is what you care about, integrity. That's what you really care about. And so it's the right approach. Well, we do want both, right? We want both integrity and confidentiality. So let's think about what the combination of the two might be, what that might look like. An information flow model specifies how information moves through a system. And it can be descriptive. I can say this is where the information goes. It goes here and it goes there. And it can be prescriptive. The information is only allowed to flow here and it can't flow there. Right? And so the models we've talked about do a little bit of both. They say I can read up and I cannot read down, or the opposite. And there's a few terms that we need to pull in from information flow that are worth thinking about. One is a source. A source is where information enters the system. Where information is being used, it's a sink. So I pull in information from, let's say, satellites or cameras, or I scrape the web, and then I turn it, and that's my source, and then I turn around and I use that information to produce some kind of intelligence product. That process is the sink, where the information goes to then be used. Through the system, it travels on channels. We've already talked about the idea of channels. And as it does, it can be transformed. It can be processed. We can merge data. It's called, right? That's the idea of data fusion. I have a map. I have imagery. I have maybe some other kinds of sensors. I can fuse that information together to produce a new intelligence product that flows through the system. Bell-LaPadula and Biba are information flow models, and they're basically state machines. And they have constraints, and they're in the form of those red X's we saw earlier, prohibited information flow. So let's put the Bell-LaPadula and the Biba side by side, and you can quickly notice Bell-LaPadula specifies no read up, Biba specifies no read down. Now, over on the left, it's all about confidentiality. Over on the right, it's all about integrity. So the question I have is, can we have both? We want both, right? But are they in conflict? From this image, it looks like they might be in conflict. But we want both, right? Picking on right, Bell-LaPadula specifies no write down, and that's to preserve confidentiality. Biba specifies no write up to preserve integrity. If we want both, we do want both. Do we have to disallow everything? Right? So give that a little bit of thought. There's a trick behind this, but give that a little bit of thought. Now, modern systems have a lot of different levels of security and different ways to implement it. There are permissions on files, and there are access control lists, and there are groups, and there's a whole bunch of different ways to implement and manage access. And we need a way to accomplish both write up and write down, and read up and read down. And the way we typically do it is maybe not ideal. We allow write down, but not up, and read down, but not up. That seems like that breaks everything. And we can't read or write up, so we have to have a super user who's up at the top who can then do all the things that we can't do. Well, once we have a super user, we have an obvious place to attack the system. And so if you ask what can go wrong with having a super user, you know all the things that could go wrong and the things that go wrong. Over on the right is only loosely connected, but I think it kind of illustrates an important point about security. So I am at the prompt and I type rm-rf/ remove the root folder. And RM responds, it's dangerous to do what you want to do. That's dangerous. Don't do that. It's a bad idea. But if you want to, put the switch on it and then I'll do it. So it's told me how to override the failsafe that's protecting me so I can then go and do that. I've always been entertained by cases where I try to do something dangerous, like, no, you can't do it. If you want to do it, here's how you do it. So, anyway. This new homework due on 17 September. And the homework is to take the two models we looked at and apply them. So consider the Biba and the Bell-LaPadula model. Now, we have some containers, alpha, beta, and gamma. Alpha has top secret data, but from an unreliable source. So high confidential data, low integrity data. Beta has secret data from a reliable source, so medium confidentiality, medium integrity. And gamma has confidential data, but it's from a highly reliable source, so low confidentiality, high integrity. Those are your containers, your objects. Alice has an active top secret clearance. Bob holds an active secret clearance. Eve holds no clearance. Eve has none. Now we assume all three are reliable, but not highly reliable or unreliable. So they're reliable, not highly reliable, not unreliable, just reliable. So we know where they are in terms of their confidentiality, what kind of clearance they have, and where they are in terms of their trustworthiness. Okay, how we rate their integrity. What access should Alice, Bob, and Eve have to each container considering only the Bell-LaPadula model? So think about the Bell-LaPadula model. It deals with confidentiality, so you only have to think about the confidential parts. What access should each one have to each container? What access should Alice, Bob, and Eve have to each container considering only the Biba model? Consider only the integrity aspects of this and tell me what kind of access they should have, right? Read, write, read and write, or no access. And if you apply both models, what access should Alice, Bob, and Eve have to each container? Now, when we're applying both, the question is, well, this one says I can read it, and this one says I can't read it. What do I do? Well, we only want to consider where they are disallowed under one of the models. If one of the two models disallows an action, then we consider that model to be disallowed, right? It's the assume none, right? So we assume you have no access unless it's explicitly granted by both models. All right. Create a table for each one of the things above. So you have 3 tables, and then you have a row for each subject, a column for each container, and then you put read, write, or none in each cell to indicate the access they have. Turn that in. That's your homework. And that's it.